open a new schematic. So that will come to this page, and few components are listed here, but if you want anything which is not like here, there is a resistance, capacitor, inductor, diode, but anything other than that, only 4 components are listed here. You click on the component icon, this one, and then you search here whatever you want. So few ICs are also there, transistors are there. So for doing the characteristics of an Nmos transistor, we need Nmos. So you just type Nmos, and it come in 2 variants. One is Nmos, simple Nmos, which is a 3-terminal device, okay, gate, source and drain. But we would choose Nmos 4, which is a 4-terminal device. That's what we learned. There's a gate terminal, source, drain and a bulk terminal. If you want BJT, you can choose NPN. Okay, so let's take this Nmos 4, and you can place wherever you want with the help of mouse, and you right click, it will go away. So you left click, it will be placed. You right click, that will go away. Then in order to perform characteristics, we need voltage source, because there are 2 voltages that are important. One is the gate to source voltage. So for that we need to again go to the components, type voltage, so this is voltage, and we need 2 voltage. So I left click one time, and then I click it again, then I click right, so it will go away. So you can place as many number of same component as you want by doing the left click, but if you want to stop doing that, then you click the right click. So if you have access to good internet connection, you can immediately, right now itself, you can download and start doing with me. Otherwise you can just watch it right now, and then later you can do it. And then you need to make connections. So for making connection, you go to this wire symbol, which is shown like a pencil, and then click on it. Then you will have a cross lines, and your cursor is wherever is the cross line. So you bring that cross line to terminal where you want to start joining, and then wherever you want to turn, you click it once, and you just go till where you want to go. And then okay, so I have given the voltage positive point to the gate, and negative point I am just wanting to connect. I gave it to source. Now the bulk usually is connected to the lowest voltage point in the case of Nmos. That is something that you need to remember. So in this case, the lowest voltage point is the source, so we connect it to the source. Second voltage source, we want to connect it between drain and source. So make that connection. Okay. Now we also require a ground. Okay. So ground is also a component that is available here. Click on it and bring it here. Okay. And again join the ground. Hope you can see everything what I am doing. If you want to readjust the schematic, you click here at this point. So zoom. So it will enlarge the circuit in the entire space that is in front of us. You want to minimize, click here. Alternatively, you can scroll the mouse also if you have a mouse. Okay, so to the full scale you can bring it here. If you want to further magnify, you can do this also. Okay, now to plot the characteristics of any device, what we need to do is do the DC analysis. So before we specify the analysis type, we also need to specify some details about the Mosfet length and width. Okay, so here if you specify it, it will take that length and that width. So usually the smallest feature in the Mosfet is length, so that you can say you give it as 1 U. 1 U means it stands for 1 micrometer, and width you can give us 2 U, this means 2 micrometer. And similarly you can specify the drain area, source area, drain perimeter, source perimeter, all of this. But right now I am only giving length and width. Okay, if you don't want to give that also, it will come whatever is the default value. So that way we are specifying the Mosfet. And then anything else here? Okay. Yeah, so we specified the length and width of the Mosfet, and then now we need to specify the voltage source. So voltage source, I give DC voltage source because I am doing characteristics. We apply DC voltage source. I can give that as 5 volt. This one also I will give as 5 volt. If I want AC voltage source, then you right click and you have to go to the advanced and then click on that. You can give a lot of different types of voltage sources available here. You can specify the frequency, amplitude, but right now we are giving DC voltage source, so it's good enough for DC characteristics. Now we would simulate. So if you go to simulate, there is a control panel. Okay, so this is one way to proceed, otherwise you just run the simulation. Okay, that the easiest way is you just run the simulation. So that is this run symbol here, and here you need to go to DC sweep, and first of all you need to give the name of the voltage that you want to change. So I'm going to specify V2, and I want to see, just like in the last class I derived and plotted the drain to source current as a function of VDS and VGS. So V2 is basically VDS. So I want to plot the drain current as a function of VDS. I choose linear scale. That depends upon what type of graph that you want to generate. Usually we prefer linear scale for the graph. And then start value, so we'll start from 0 volt, and then it will go to 5 volt. Increment, if you want a very smooth curve, give a smaller increment, say 0.01, so that you will get for each step of VDS by 0.01 you will find out the corresponding current, and then it will all be joined with a smooth line like a curve. So this is the graph that we want to plot with respect to V2 change. Now if you want multiple such graph for different values of VGS, then we have to give the source VGS value also, and also linear. We would start from 0 and we will go to 5, but this we will go in steps of say 1 volt, steps of 1 volt. Okay. So let's see what will happen. Okay, so I have basically implemented that command. This is the command for simulation. DC V2 is varying from 0 to 5 in steps of 0.01, and V1 is varying from 0 to 5 in steps of 1 volt. Now to get the curve, as you can see that the x-axis is already the whatever is the first quantity that we specified, which is VDS. It varies from 0 to 5 volt. Now I can move the cursor on the top of this terminal, drain terminal, so there will be a change from cross to a different. Exactly what does it show, I am not able to see it, but there will be a change when you bring it into the terminal. If you bring it anywhere else, you will get this pointer kind of. For voltage, that is what you need to choose at a particular node if you want. So you bring that on any point and then press there, it will show the voltage there. Okay, but what I want is the current. So this is the current that we get. Let me just show these windows side by side. Okay, so this is the circuit, and this is basically the currents. If you look at it, is in microampere, 50 microampere, 100 microampere, like that. So different curves are there. So what does each curve stands for? How many curves are there? Green, blue, then red, cyan, purple and grey. So altogether we have 6, and they correspond to the steps of VGS. So VGS is varying from 0 to 5 in steps of 1. So 0, 1, 2, 3, 4, 5. So there are 6 VGS voltages for which we are plotting this characteristics. This is called the output characteristics. Okay, so as I told in the last class, so if you look at the output characteristics, you can divide it into 3 regions. The first region, small voltages of VDS, if you look at the curve is like a straight line. So if you keep a scale, you can see that it is like with some slope, you can see straight line. For example, the top curve, if I keep a scale on the top of it, roughly up to 1 volt I get a straight line up to here. Up to here it's a straight line, but then the straight line should continue like this, but the actual curve is bending, and that continues until somewhere here around 4.8 volt. Now if I look at the red line, same thing I can see there are 3 regions. So if I put a scale near to the origin, I will get a straight line, but this time maybe only up to 0.5 volt the straight line is valid, and then the curve begins to bend because of the quadratic term coming up. So from 0.5 onwards the curve bends until say 1.7, 1.8 voltage. It is a quadratic region. So there is a linear region, then there is a quadratic region, finally there is a saturation. That means current is not changing at all. With respect to the increase of VDS, current is not depending. Okay, so that's the saturation region. So we have the linear region, quadratic region, and the saturation region. So this is one characteristics, and we have plotted it for different values of VGS. So as you can see, when VGS become larger and larger, we have larger current. So that you might have expected, because for example the first curve is for 0 VGS, we don't expect any current. Why do we not expect any current? Because we don't have any inversion happening with the 0 voltage of VGS. It requires at least some threshold voltage. Whereas when you come to VGS equal to 1 volt, there is a small current. So that means a small layer of inversion is there underneath the oxide layer, through which current will flow when you apply VDS. But current quickly saturates because pinch off would take place. Okay. But if VGS is larger, then the pinch off, that means the saturation will happen much later. So that is what this characteristics. We will go into the theory of it a little more in the tomorrow's class. But so this is the characteristics that we get, and you need to get yourself familiarized with it and understand it. Now another very important thing is how does the saturation current depends upon the VGS. The saturation current, if you look at, that means the horizontal flat line, if you project it to the y-axis, you can measure the current. So that is called the saturation current. That current is independent of VDS. It depends only on VGS. So how does that depends upon VGS? And we will see the expression for it in the next class. But one thing is very clear: the horizontal lines are determined by the value of VGS. It is not determined by VDS. So the plot of the saturation current with respect to the VGS versus ID. So this is VDS versus ID, but I can alternatively find out a curve which is VGS versus IDS versus VGS. Okay, that means the input voltage versus the output current. And that characteristics is popularly called as the transfer characteristics. Now, in order to plot the transfer characteristics, if you want to view, only one of this line or something like that, then for example corresponding to step 4, you want only that, then you can just choose it like this. So view, select steps. If you want to select all, you give select all. Okay. So there are certain things that you can do here like that. Okay, so let me just close it over. And then I'm going to modify the circuit, and what I'm going to do is I'm going to remove this so if you want to remove anything, you take this cut symbol. Say I can do this, I can do whatever I want to remove, I can do that. So now what I'm going to do is I'm going to connect VGS and VDS. That means the gate and the drain terminal I'm going to keep it same. So let me make that connection. So this is the connection. What I have done is basically join the gate and the drain terminal. Okay, so this is intentionally I am doing that, and then I'm going to do the DC characteristics. That means I change the value of V1. There is only one voltage source now, that I can vary in steps, small steps. And then what I would plot is the drain current. I will plot as a function of this voltage, and this is VGS also, this is VDS also. Okay. Now if VGS or VDS is equal to VGS, what does it mean? It means that the saturation is ensured. If the VDS value is kept same as VGS value, then the saturation is ensured. How do we ensure that it will operate in the saturation region? Now if it is ensured that it is going to work in saturation region, then what the current that I will get is basically the saturation current. So my idea is basically to see how the saturation current depends upon the value of VGS. So I have modified the circuit, connected the drain and or short circuited the drain and the gate in order to ensure the saturation mode of operation, and it is very easy to see why it would work in saturation. Saturation usually happens at a voltage, VDS voltage, which is larger. Okay. Now for small VGS, saturation happens earlier, like as we saw in the last diagram, the plots. For a smaller VGS, saturation happens earlier, but for larger VDS or larger VGS, saturation takes a little more time. For example, the top curve corresponding to VGS is equal to 5 volt. Just before the VDS became 5 volt, around some 4.5, 4.8, that is the point at which we got saturation. Whereas the smaller value VGS, say VGS equal to 1 volt, it got saturated much early, say at around some 1 or 2 volt it got saturated. So if we keep the VDS value above or equal to VGS, then it will always saturate. Okay, and we would see the theory of it in more detail in the next class, but now let us plot it. So again, run the simulation, and what we want to do is basically the DC sweep, and V1 is that source, linear sweep, starting value 0, stop value say 5, and increment 0.01. Smaller steps, better is the clarity of the plot. Okay. Again I will change the window to vertical splitting, and I bring the cursor until I get the drain current. So this is the curve that I will get. These are the saturation curve. So x-axis is now VGS, which is same as VDS, but VGS versus ID is what we call as the transfer characteristics. So this is the transfer characteristics, and as you can see that it is basically a parabolic curve. Okay, so it's like a parabola, and we will see this derivation for this parabolic relationship between VGS and IDS. But right now, so that is only one curve. You cannot have multiple curves for this, because we are taking saturation current which is independent of VDS. So you just need to apply a voltage which is enough to saturate. That's the only criteria. And the simple way of doing it is to make VGS same as VDS. Okay, so that is one thing. Now same thing we can do it for Pmos also, but there are some differences. Just like I told in the case of Nmos, that source, by definition it means it sources the charge carriers. In the case of Nmos it is electrons. So the source terminal give out the electrons, which are the charge carriers, moving through the device, and it comes out of the device at the drain terminal. So electrons are flowing from source to drain inside the Nmos device. Similarly, if you take a Pmos device, the charge carriers are going to be holes, and again the source is going to give out these holes, and then they are going to come out at the drain. But the direction of current will be different in both devices with respect to the motion of charge carriers. If electrons are moving from source to drain, your current is going to go from drain to source through the device. Whereas if holes are going to go from source to drain, the current is also going to be from source to drain. Okay, so the current is in the same direction as the flow of holes through the device. Okay, so let's cut this away, remove this component. So choose this cut symbol and then remove this everything. Going to, okay, let's delete everything. Alright, so everything is gone now. So I'm going to take a Pmos from the library. So I type Pmos and I'll choose Pmos 4. This is going to be a 4 terminal device. I only need one. Okay, so again it has 4 terminals, gate, then source, drain and bulk. 4 terminals are there. Now the voltages that we are going to give are such that in the case of a Pmos device, source is going to be at higher potential, because the current is going to be from source to drain through the channel, because the holes are going to be sourced from the source terminal, and then it is going to flow into the drain terminal. So therefore it is important to apply the source terminal with the more positive voltages. There are multiple ways we can do it. One is to connect the battery such that the positive terminal is of the battery is connected to the source, and the negative terminal is connected to the drain. Or wherever you connect the positive terminal of the battery, that is going to become the source for Pmos transistor. And earlier I told we need to connect the bulk for an Nmos to the lowest voltage in the circuit, but here I would say it should be connected to the highest voltage in the circuit. So that is a convention. And so whatever is the source voltage, which is going to be positive compared to the drain voltage for Pmos, so we need to again connect it to the source. So both cases we are connecting to the source. But if there is another voltage which is available higher than the source voltage, then the bulk is to be connected to that voltage. Okay, so let's take the voltage source. We need two voltage source. One for gate, one for drain. Okay, so suppose this is my drain and this is my source. So source has to be more positive. In other words, VDS should be negative. So I am going to connect this one like this. Okay, and then so it should also be connected to the more positive voltage. Now how do I make it more positive? What I need to do is I right click and put here -5, which means that my bottom terminal, which is my source, is going to be more positive compared to the drain terminal. I gave minus. So it's like putting the plus of the battery downside and the minus of the battery on the upside. So if plus is put on the downside, that will be more positive. Okay, similarly I need to apply a negative voltage to the gate. Okay, and negative with respect to again so let me connect it to okay. So the way I have done right now, it looks like I have given positive voltage, but then like before, what I can do is make this voltage negative. Okay, which means that my gate voltage is going to be negative with respect to the source. So source is the highest voltage point, and with respect to that the drain voltage is negative and the gate voltage is also negative. So this is a difference with respect to the Nmos and Pmos. So in a Pmos transistor, the bulk region, okay, the semiconductor substrate is basically made up of N-type material, and then we need to apply a negative voltage to repel those electrons, create the depletion initially, and then if you apply sufficiently larger negative voltage, we will attract holes there, and the holes will form an inversion layer. So for that to happen, we need to apply negative voltage with respect to the bulk as well as the source. And there will be P plus region which will be joined by this inversion layer, through which current can flow when you apply a drain to source voltage. So drain will be kept negative and source will be positive, because the holes are going to flow from source to drain, and that is the current direction also. So for that reason, source is going to be positive compared to drain. Okay, so the highest voltage point is the source here in the circuit. Earlier source was the lowest voltage point for Nmos, but for Pmos we have the highest voltage point in the circuit is the source terminal, and therefore the bulk is also connected to the highest voltage point. We will see later that digital circuits with the transistor, CMOS, PMOS and Nmos transistor, in which there are even higher voltages than the respective source voltage. So for PMOS we need to connect them to those points. For Nmos it is also possible to find a lower voltage point than the source point, so we need to connect the bulk to those points. It is better. Okay, so now let's plot the characteristics. So you click on run and then choose the DC sweep. As before, we will choose B2 because we want to plot the ID, that is a drain current, as a function of VDS. So VDS is negative, it goes from 0 to -5 in steps as small as we want, and then second source should be varied, that is our V1, our input. Linear start value, again we can give 0 and then up to -5. So increment I think specify it is starting from 0, so I have to go in negative step, so -1 I will give, -1. So earlier one I didn't put the minus sign, so let me put the minus sign. Okay. Okay, this circuit does not have a conduction path to ground. That means I didn't put the ground terminal, which is also important. So for every circuit here, we need to have a ground point. With respect to which all other voltages are going to be mentioned. The drain and the source voltage are going to be. So this is mandatory for every circuit in LT-Spice to put a reference point. So with respect to this reference point, which is our source point, source is the reference, both in Nmos and Pmos, source is the reference. But difference is that in Pmos, source is the more positive voltage. All other voltages in the circuit are negative than the source voltage. Okay, now it should run. Let's put the windows in parallel. So what I am interested is in the drain current. So this is how it looks like. So you can see that negative current. Negative current means actually the current is going into the terminal, not coming out of the terminal. So whenever we take a terminal current, I think it is assumed that the current that is current is going, it is assumed that the current is going into the terminal, but here actually the current direction is from drain to source. Source drain. It is actually coming out. Okay, so the lower point is the source. From source it moves to the drain, and therefore the current is going from bottom to top through the device. So it is actually coming out, but what is plotted here is the current going into the terminal. Since the actual direction is coming out, so we have negative. And you can see the VDS variation from 0 to 5 volt, as then more and more negative voltage. So actually if we plot it in a graph, this will be appearing in the third quadrant, right? Because the current is negative, voltage is also negative. So Pmos characteristics will be in the third quadrant. Okay, everything is as before. There is a linear region, then saturation region, and then there will be quadratic region in between. Linear, quadratic and saturation. The green curve is corresponding to zero current because VGS is less than threshold voltage, and there is no inversion layer of holes created with that VGS is equal to 0. So you need to make VGS negative. So the threshold voltage is negative. So -1, already inversion layer is created, but you can see that it quickly gets saturated from here onwards. The red curve, it takes more time to get saturated. Cyan curve takes more time, roughly -3 volt to get saturated. Purple curve, more than 3.5 volt to get saturated. So as VGS become more and more negative, it takes more VDS to get saturated, that you can see here. Now, like before, I can again do what is called as the transfer characteristics. So I need only one source, so I can remove whatever I don't want. Then I connect. Okay, so that means like before, VDS and VGS are same, and under this situation it satisfies the condition for saturation mode of operation, and we will see why in the theory class in more detail. But right now you just accept it and then let us plot it. Again we need to do DC sweep. There is only one voltage, which is V2, which is going to be linear, and then start is 0, stop is -5. I go in steps of -0.0, say 2. You want more clarity, it is 0.1 is also better. So what I want is the drain current. So as you know, the drain current is actually coming out of the drain terminal, but here it is showing negative because the direction convention is taken as going into the terminal. Okay, let's put it side by side. Okay, so now what is the threshold voltage? That is a very important question, and you can see that the current is 0 till some value of VGS, and then it starts. So the point at which the inversion layer is created, that is the point on which the current starts. So the threshold voltage here is determined by the point from which you have the current starting. Okay, so if you project that, maybe something like 0.25, okay, some roughly here 0.25 is the voltage where you have. If you magnify it, you can see like this. So somewhere here, so initially current was 0, so but then it start becoming non-zero at some point of time. So that voltage is what is called as. So in the transfer characteristics, same thing you can do for Nmos device. You can look for the point at which current become significantly large to be shown in the characteristic curve. So that is what is threshold voltage. Now if you want to specify the threshold voltage in the Mosfet model, that is also possible. So here I have not specified length, width. So if I change the length and width, this current is going to change. So let me show you that also. And this is going to be 10. So let's see what is the change in value. I suppose the current will increase now. Okay, so it has gone to milliampere right now, because I have increased basically the W by L ratio. I made it 10, so the current has increased. So it is now on the scale of milliampere. Earlier it was micro. So that you can do by changing the. But here for this particular Mosfet, the threshold voltage is seen to be very, very small. You see. So if you want to specify the threshold voltage, there are ways to do that. To do this, there's a SPICE directive. So dot model some name you can give, Pmos 1, okay, so I think I should give this name M1, then I say Pmos, you can give multiple things, but let me just try this. It is 0 is equal to 0.8 or minus 0.8. So I specify this. Let me run again. Let's see what happens. VT0 is equal to minus 0.8. Okay. So it has not changed. Let me try it again. If I right click, I can go directly. Let me just see this KP equal to 100 micro. VT0 is equal to this. Still there is no change. Let me see, put Pmos here also. Let me try it. Yes, now it is come. So it's not M1 that I should give. I should give this Pmos. Okay, so you can now see that the current is remaining. The current is remaining 0 till some longer time or longer voltage. See, I gave 0.8 as the threshold voltage. So till 0.8. I think earlier it was 0 voltage. Although it is not very clear. So if you magnify, you can see that. So 0.8 is here. So earlier this was like the situation at 0 voltage. So now you can see that it is at minus 0.8. You have, although it is not clear whether the current is becoming non-zero there, maybe there is a very small current. So it's too small. Okay, so it's not much visible, but definitely the model that we have entered has been taken in. The same thing you can do it for Nmos also, though I did not show. There you specify, instead of Pmos you put Nmos, and then VT0 should be plus 0.8. And what is Kp? Kp is some parameters which is there in that current equation. Like if you remember the current equation that we derived, it was like mu Cox, then W by L, etc. So Kp is basically mu Cox, those constants which are there. Okay, so that is Kp. We will look at it, those constants in more clear detail in the next class. So I hope you have understood what we did today. We took an Nmos and Pmos transistors and we plotted their characteristics. One is the output characteristics and the other is basically the transfer characteristics. And from the transfer characteristics you can identify what is the point at which the current begins to flow, the point at which inversion is happening, and that you can specify using the spice command. So in order to specify the spice command, you go here and type the spice command, and I will give you some helps to learn about spice command later. Okay, so that's all for today, and you do it, but you apply this directive, spice directive, for Nmos also, and find out its or verify whether what you are giving is coming as your threshold voltage. So for Pmos the threshold voltage is negative, for Nmos the threshold voltage is going to be positive. So VT0 you give it as positive voltage for Nmos. There could be more parameters that you could enter if the model has to take into account of it. So the spice model is basically the model that it will make use in order to produce the result. Okay, one more thing I'll show you. Okay, so let me just go back to the earlier characteristics. Have saved it. Okay, let me just see. Control is yeah. So this was my earlier circuit, and then I'm going to do the same thing. I just did undo and came back to the earlier wiring, and now if I introduce the spice directive here, but this time I want to write model say Pmos then I can give more directives. So I'm giving VT0 minus 0.7 to 1.5. We can give that. Okay, so 0.6, and then another thing I can give is lambda. Okay, I did not teach you about it, but right now let me just show you. Lambda equal to say 0.1. I just want to show you some effect of this. Lambda 0.1 may be a little large, but let's see, just to see what is going to happen. So what is going to happen? You see that the saturation level, if you look at, there is a slope now. So I just specified that slope. Okay, earlier it was completely horizontal. That was like lambda equal to 0, but now lambda is 0.1. So if I give 0.01, then it will be still lesser slope. Okay, now the slope is much smaller. Still slope is there, it is not entirely horizontal. So lambda is a parameter which tell you the slope in the saturation level. So even after saturation there is a slight dependence on VDS, it's not like completely independent. Lambda equal to 0 is an ideal case, but practically there will be non-zero. We will look at it later. Same thing you can do it for Nmos transistors also. Okay, and another thing is, if you do the transfer characteristics again, you will see that so this is our Nmos. So if I want to do the transfer characteristics, model Nmos now, Nmos. So one Nmos here is the name that we give here for this, and the other Nmos is basically to say that it is Nmos transistor. So if you change this name, here also you have to change that. Okay, so now what we can do is say, I will just show you the effect of PT0. Say it's equal to 0.7 and then lambda equal to 0.05. Okay, so that is a parameter into optical. Okay, so you can see that there is a slope. This is Nmos characteristics. Everything is positive, and then the slope is positive here. Everything is in the first quadrant. Okay, but you can't see really the 0.7 effect in the output characteristics. For that you need to go to the transfer characteristics. Okay, so that you can do it yourself, and leaving it to you. Alright, I will stop here.